Now that we have a review of Fourier series, let's look at Fourier transforms as a limit of Fourier series under some specific understanding of limit. So we have a Fourier series expressed as a complex exponential by infinite sum of coefficient time complex exponential, with an understanding of what the coefficient is as an integral over our period of fx times the complex conjugate of the same exponential, with this 1 over 2L that is just a rescaling. Then if we plug Cn into the definition of fx, we have this formulation of fx with respect to itself. So fx being a by infinite sum of a constant times an integral times a complex exponential. We want to explicitly state how this integral depends on the choice of kn that we have made. We also do some rescale. We multiply and divide by 2 pi at the beginning just to have some right coefficients at the start. But now I have introduced this f hat underscore L. L is the width of our integration interval, and I want to make it explicit that this is depending on the kn that we are choosing. So here is the definition of f hat. There is a problem in the typo in the definition. There is an omega on one side and a kn on the other, but that I will correct when putting the slides out. And with this new definition, we can write fx as a 1 over 2 pi by infinite sum of pi over L f hat kn. We have the same problem in the definition of f hat, that omega on one side and kn on the other. We would now want to restrict ourselves to specific functions. So we want to restrict ourselves to functions, no more functions that are periodic on minus L to L, but functions that tend to 0 as x tends to infinity, positive or plus or minus infinity. Or even stronger, we're going to be using it for doing the computations in an easier way, functions that are exactly 0 after a certain threshold, in the positive and in the negative direction. These functions that are 0 after a while, so are non-zero only on a finite section of the real line, are called compactly supported. So we have this definition of f hat L omega, and we want to think about it for L tending to infinity. But we have said that f is 0 for the absolute value of x too big, so that we can understand how this integral is well defined when we're letting L tend to infinity. How do we then interpret the infinite sum that we're using to define to reconstruct f? So if we look at it, there is this f hat kn. So we're doing a bi-infinite sum with some coefficients, a coefficient that depends on L, and a function that is computed only on kn. Can we interpret this in some more intuitive way? So in order to do that, we're going to be reminding ourselves of Riemann integrals. The idea that the integral of a function between a and b is the limit of the sums of these rectangles that you can compute under the function itself. So if you take the interval AB, you divide it into subsections, you create a rectangle. You can choose to create this rectangle such as the average or the top or the bottom, but if you let the width of the rectangle tend to 0 and you keep summing the areas of all these rectangles, then you tend to the definition, by definition, you tend to the value of the integral of the function. So here I wrote it as two different formulas, either a limit for the number of rectangles tending to infinity, or the limit of the width of the rectangle tending to 0. Clearly that is the same thing. But when we are looking at the width of the rectangle tending to 0, we have a formulation that is closer to the one we're seeing in our previous definition. Either of them is called a Riemann sum. So if you're looking at the definition for the width of the rectangle under your function tending to 0, you see how that limit does look quite similar to the limit we're looking at. We have something divided by L that behaves like dx, and something that is f hat kn e at the I kn, so a big function that is evaluated, well, at kn's they're getting closer and closer the higher L is. So you see how there is a correspondence with the Riemann integral. So with this, we can understand how when we're taking the limit for capital L tending to infinity, so the width of our interval that we are integrating over is tending to infinity. And it makes sense because we want our function over that integral to be tending to 0 at infinity. So we can take this in infinite. Then we can replace the infinite sum by an integral between minus infinity and plus infinity of the element we were taking the Riemann sum of. So there is this f hat omega e at the I omega x d omega. So we have replaced kn, that is only computed at some countably many points, by this f hat omega, where we still have an understanding of what f hat omega is. So f hat omega is itself an integral from minus infinity to plus infinity of our original function times ei omega y dy. There is a minus in the definition of f hat omega on the exponent, coming from the definition of the exponent before. There is another typo in the slides. So in one direction, we're talking about Fourier transform, when we're going from f, that is a function we know, to f hat. And in the other direction, we talk about inverse Fourier transform, when the knowledge about f hat transforms back to the knowledge of fx. The idea when we're talking about Fourier transforms is following very closely the idea of the Laplace transform. We hope that by jumping between the information we have about f and the information we can have about f hat, we can gather more information. So we start at fx, we apply the Fourier transform, we retrieve f hat, we retrieve some information about f hat, and we're able to come back with the inverse Fourier transform. This is a slide with all the formulas. In both cases, so both when we're looking at fx and when we're looking at f hat, the domains of the unknown is the whole real line. So x spans the whole real line and omega spans the whole real line. And we have an explicit formula to go from f to f hat and from f hat to f that involves an infinite integral and a complex exponential. As we did for the Laplace transform, we have a compact notation that is just this calligraphic f of the function we're looking at, with -1 in case we're talking about the inverse Fourier transform.